Well, we are now ready to work the homework for section 1.2, and as often happens, there is some revision from the lecture video. In this particular section, there's a number of revisions, so please pay careful attention to this list of items. We're still going to do the Taylor expansion on the log of 1 plus x, but we have 5 separate tasks to complete problem A. The first one is to form the series solution, meaning the Taylor series solution, using a constant plus 3 terms. That'll get you through part 1. Then we're going to generalize this so that you can derive an arbitrary, what I call kth term for the series. K can be anything. It could be second or third term, but it could be fourth or fifth or 10th, or any finite number k will work. So you need to come up with the appropriate formula using term k. After that, I'd like you to create an Excel file that has 3 columns. The first column will just be your k number, starting with 0. So row 0 will represent the constant term, and then rows 1 through 10 will represent the first 10 terms of the Taylor series. You'll evaluate that about x sub 0 equals 0. It doesn't say that there, but x sub 0 is supposed to be 0. And evaluate x at 0.85, and then go ahead and develop all 11 of those terms, constants plus 10 other terms. The second column of your Excel file should contain the term itself for the kth row. And then on the third column, I want you to do a running sum of what's in the second column, which is your series. So that's what we'll do with the Excel file. I need you to create a stopping rule using the error term on the Taylor series, and you will compare that error term to an error tolerance of 10 to the minus fifth. So you have to be a little careful there, because on the error term, you have to evaluate the derivative at zeta. So it's really the kth derivative you evaluate at zeta, and zeta is locked between x0 and x, the value you're interested in. And you don't really know what zeta is. So what your job is to do there is determine what zeta should be to give you the worst case error, meaning the largest error in absolute value. And so go ahead and do that, and then create a little MATLAB code, actually P code, which will then loop through the terms until you get an error that's small enough. That's how you want to create that. For the fifth item, I'd like you to take the polynomial associated with that finite Taylor series that you've been developing and take advantage of onion peeling. On this onion peeling, we're going to do it just the same way as we did it in section 1.1, and I'll give you a few more hints on that later. For exercise 5, it's really the same thing as problem 1, except maybe not all these steps. So just go ahead and create the Taylor series for the hyperbolic cosine. If you're unfamiliar with the hyperbolic cosine, look it up in Wikipedia. It's a very simple combination of e to the x and e to the minus x. Do that to 4 terms past the constant, so the constant plus 4 terms, and then take your polynomial and try to estimate the hyperbolic cosine of 0.7 from that. Go back and look into either MATLAB or your calculator if it has hyperbolic cosines, or in Excel, and find out what these programs tell you that the hyperbolic cosine of 0.7 is, and compare that to your result and see how well it does. And finally, for extra credit, I want you to go back and look at the Taylor series for e to the x. It is on page 25 of your book. If you don't have your book, it's pretty easy to create that Taylor series, so just go ahead and do it from the formula. If you are in the range from 0 to 1, then I'd like you to tell me how many terms are needed, not counting the constant, but terms beyond the constant, are needed to get 15 significant digits. So we'll talk a little bit on the hints on how to do that. So this is going to help you. If you don't have your book in front of you, this is the Taylor series. This is really all you need to accomplish most of the problems, except for the error term, which we'll talk about in just a bit. And let me help you get through problems 1 through 3 on part A. First of all, you have to evaluate the function at 0 because x0 equals 0 for this problem. Well, that's just the log of 1 plus 0, which is the log of 1, which is equal to 0. So I have just given you this term right here for free. You do the rest of them. You'll need to calculate the first derivative, second derivative, third derivative, and maybe fourth derivative, and so forth, and then get an arbitrary kth derivative that you will use. So find the first derivative. What is that? What's the second derivative, third derivative, and what is an arbitrary expression for the kth derivative? Then just plug 0 into all these numbers and come up with constants associated with that. And that gives you all of the coefficient terms that you need. x0 is 0, so you can just take that out, and you should have a nice polynomial. Well, that nice polynomial really can be simplified more if you look for terms that can be canceled. So please simplify the expression and make sure that it is as straightforward a polynomial as you can create. Now that's going to take care of parts 1 and 2 for you, because part 1 you just needed 3 of these terms plus the constant, and part 2 you needed to get an arbitrary kth term on there. Well, you've done all that. And then on part 3 you're just building an Excel table using this formula. So really this hint covers you for parts 1, 2, and 3. How about parts 4 and 5? This is where we start taking a look at the error term, and the error term looks just like the kth term that you already created, except you have to evaluate it at k plus 1. That's the first change you have to make. The second change you have to make is you evaluate the derivative at a point zeta, which most unfortunately you not only don't know, you can't know. But what you do know is that this mysterious value zeta lies somewhere between x0, which in our case is 0, and x. So what you have to do is come up with a conservative error. Find out where in this interval, whether it be close to 0, or it is 0, or whether it be close to x, or something in between, that would make the error term maximized, particularly the absolute value of the error term. So that's what you're really going to need to do the problem. So here is our error term. In case you don't have a book handy, you have it all right in front of you, and you are going to evaluate the k plus first derivative at zeta and use the rest of the term as you should to get this error term of k plus 1. Okay, where your derivative, you need to figure out what that's going to be. And again, it's going to be an upper bound. Really, it's an upper bound on the absolute value of e, and you figure out what value of this derivative produces that upper bound. You're trying then, once you find that bound, to come up with the number of terms that will keep the worst case scenario of the error below some specified tolerance. We're calling it epsilon. Okay, so in other words, what value of k would you need to calculate so this upper estimate of the error is less than the tolerance that we have? Okay, and finally, to help you with the fifth problem, it's looking at the polynomial in terms of our onion peeling exercise. So kind of going back to section 1.1. And I thought the easiest way to get you started on that is to give you a similar Taylor expansion of a different function and see what you would do with that, and then see if you can kind of morph that over to the appropriate Taylor expansion for the log of 1 plus x. So you'll find that on the log of 1 plus x, if you get it right, you're going to get these oscillating plus and minus signs occurring, and you'll be able to generalize that through some -1 to some power. It'll look a little different than this, but look very similar. And see if you can be factoring out x's in such a manner so that when you're done, you just have a series of minus signs. You might want to take a look at this to convince yourself that this highly nested polynomial is exactly as the same as the one we started with, and then use that as an example to help you with the fifth problem. Okay, so that's your onion peeling exercise. On problem B, there's really nothing more for me to tell you other than we're switching over to the hyperbolic cosine. We're still using x naught equal to 0. We still have the same Taylor expansion, same error, but of course the numbers are going to be a little different. If you can't remember exactly what that hyperbolic cosine looks like, you can look that up in Wikipedia. It's fairly straightforward, and it involves exponentials. So we go about and do the same thing. You have to evaluate hyperbolic cosine at 0. What is that? Take your first, second, third derivative, and kth derivatives and plug in values of that at 0. So again, just like we did before, we're doing the same thing with the hyperbolic cosine, and just complete the Taylor series just the same way you did in problem A. And then finally in problem C, our hints there is use the error term. This is almost exactly the same problem as the fourth step on problem A. Again, you're worried about how to create this error term and what are the derivatives and what value of zeta should I use. And then you want to find out how many terms, meaning n, how big n should be, so that this in magnitude is less than epsilon, where epsilon is a predefined number. Now, I'm telling you to use 15 significant digits. I didn't tell you what epsilon was, but I've kind of given it away here that if to get 15 significant digits, you better have an error less than 10 to the minus 15th. So I think that helps you create requirements for that. But now you need to write a MATLAB code using some kind of a while loop that helps you determine how many terms are needed based on that error term. This would be actually very hard to do if you just try to do it directly. In fact, you really end up with a formula you can't solve directly. We'll have other methods in Chapter 3 to help you solve what are called nonlinear roots. But for right now, it's good enough to just loop through as many times you need until you get an error that's small enough and say, voila, that's my number of terms that I need. Okay, so that completes the hints part. Give you 3 days to go off there and try to work that, and then I'll produce the solutions for you on this.